We are in the Introduction to High Performance Research Computing course. HPRC stands for High Performance Research Computing. That's just high performance computing with extra steps. So the computing part is what's on the screen right now. The university owns a bunch of computers and they're for you to use. That's for your research. So that's the point of them. And my name is Richard Lawrence. I'm a user support specialist with the High Performance Research Computing Group. I teach Python and how to use our computers, and I also teach some research skills. If you happen to need some research skills, you might be encountering me later on. So we're going to go over a lot of things today. Some of them are not as exciting. I apologize, but in order to use our clusters, like there's a foundation of knowledge that's quite broad. And a lot of it is just like, what are you allowed to do? How do I know what I'm allowed to do? So these are things we'll talk about. Usage policies, how to be a good person. References, you can find links to most of these materials. We'll remind you how to find those links. I'll talk about the computing clusters. I already showed you the pictures. I'll give you some facts. We take lots of breaks because, I don't need to talk for 2 hours straight and make my voice hoarse. And then we do some exercises. We're going to access the clusters. There's a couple different methods you can try. We're going to learn elements of a computing environment. So in Linux, environment has a specific, that's a jargon word. So we're going to learn how that works. And then after we learn the environment, we'll take a break. Then we'll practice. Then we'll practice learning how to use cluster computers, and then another break because it's kind of long before we do the actual exercises for using cluster computers. And we have usually whenever we do anything, we'll do it like 2 or 3 different ways, just to make sure you find one that's comfortable for you. So even though it doesn't look like much here, it is going to take a while. That's just the nature of being a student. So the first slide here, usage policies. I have to read these to you, but they're boring. So go ahead and fall asleep if you like. It is illegal to share computer passwords and accounts. So for HPRC, you use your same net ID that you use for everything else. So if you're already comfortable with using your net ID, there shouldn't be any surprises here. It's literally the same thing. Then it is prohibited to use HPR clusters in a manner that violates the United States export control laws. Normally, that's not a problem because mostly what we use is open source software. Here at the university, we like sharing, so that's the open part of open source. And we also like free, which is a natural byproduct of open source. So if you just go with what everyone else is doing, it's not going to be a problem. But if you are asking for something that's particularly different, where you have to have a license, then it starts to become a possible concern. So anytime you're using software, you really need a license to use that software. That's when you have to start thinking about this. And you'll know because there will be extra steps. So you won't be allowed to forget. And then, of course, if you're using a license, then also the company that provided the license will have their own rules. You can find more about these policies on our webpage, hprc.tamu.edu policies. Why don't we check out hprc.tamu.edu? You've probably seen this webpage before because that's how you would have enrolled in this course. There's a policies up here. You can read about acceptable use. That's the same facts I just read you, but like, in 100 words instead of 10. Education resources. So I'm a resource. I'm here for you, but in a couple hours I won't be. What do you do? Well, we publish a lot of our training materials in the form of, like, for example, this document. You can pull it up and read it along with me. It's just here at this link. So show you how to get there. You have events, short courses. And then here's the one for today. You click view details, scroll down, you'll see the same slides I'm showing you right now. There's a link you can download them. So if you want to review what we've learned, no problem. We also have a YouTube channel. So whenever we teach these courses, we usually record it. You can see the recording symbol if you're in person. If you're on Zoom, I'm just being weird. Then if I do a good job, then it ends up on YouTube. So you can go watch like previous times people taught these courses on YouTube. And a lot of the basic stuff is broken down into like 5 and 10 minute increments. So it's like, how do I log in? Just a video all by itself. So that's some people prefer watching videos. Maybe you're just like, all right, I'm out of here. You walk out, I'm gonna go watch videos. That's fine with me. I'm not gonna hurt my feelings. I'm in some of those videos. So, and then once you get to the point where you mostly know everything, but you need to look up like a specific fact, that's when you go to our wiki. So we have a wiki. It's hprc.tamu.edu/wiki. And let's investigate that. If you see up here, resources, knowledge base, that's not it. Oh well, it's on the left panel. Most of these links you can see at the bottom, they're links to various places in our wiki. So for example, if I want to learn more about the GRACE cluster, I click here, I end up on the wiki. And the wiki has a home page that just describes what types of things are in here. Most of the stuff I'm going to teach you today is literally just from our wiki, but in the form of a slideshow. So if you need specific facts, the wiki could be a faster way for you to get to those specific facts. That's enough of that for now. Oh, I thought I changed this slide. I definitely changed this slide. Okay, so I changed this slide, but somehow it's not updated. All these words are supposed to say GRACE. We're going to be using the GRACE cluster today for our examples. Last semester, we used the Terra cluster for our examples. I just decided autonomously, I feel like we're using GRACE today. They're pretty much the same. So if you end up deciding that you really do want to use Terra, you'll be fine. You can still do the exercises. I'm just using GRACE today. And I hope you choose to use GRACE because there is like one point where it matters, and going forward in the future, it's going to matter more. So if you choose not to learn that element, you'll be missing out on something that's important. So this slide is supposed to say GRACE. I somehow got the old version. I don't know what happened. Everything else is the same. So there will be a path on disk, Scratch Training Intro to, but then it says GRACE instead of Terra with a capital G. When we get there, I'll remind you what it looks like. So we'll be doing some exercises. A lot of the exercises are drawn from our wiki. Drawn from our wiki. The files you need to do the exercises have already been downloaded into the cluster computers. So this is a path in our cluster computers. So then once you log in, you don't have to upload them, they're already there. So that's how we'll do that. And then when it's time to log in, I prefer to use our portal, which is the most convenient way to log in. That's logging in through your web browser. And I'll show you a lot more about that as we go on. But if you actually just don't like your web browser for some reason, you can do the exercises by command line. If you're like, I've been using PuTTY in my Windows machine since 1995. Okay, you're allowed to continue doing that. PuTTY is like a remote login software that helps you out, and it's not great, but it'll do. Well, I like on the web browser interface because it's like click with your mouse. It doesn't, doesn't burn as many calories just trying to do basic things like logging in. So here's our 3 clusters again. So on the left, we have Terra. Terra is the older cluster, still operational for people who've been using it for years. They're still allowed to continue using it, so they don't have to learn anything new. They can just do what they're doing. If you're joining us, you probably don't want Terra because GRACE is better. Grace is pretty new. It deployed in 2021, and it has more powerful machines. It has more up-to-date software. We would prefer if you used Grace because, you know, eventually Terra is going to be retired. We don't want to have to migrate you to Grace at that time. Be like, why don't you just learn Grace in the first place? And the next cluster, which is almost done being under construction, its name is FASTER. That's an acronym. I don't know what it stands for. It's in early access, so you probably have a FASTER account if you click the button. So if you wanted to, you could log in and check it out, but not all the features are working. So if you tried to actually do your research on FASTER, you might run into a speed bump. And so at this point where you're just learning how to do things, you don't need that extra headache in your life. So probably wait for FASTER to be fully deployed before you try to use it. FASTER is otherwise very similar to Grace in terms of how you use it. So whenever you're ready to use FASTER, it'll be easy for you to do that. They literally share elements. So you're here because I assume someone told you to come here, but just in case, I will try to persuade you to come and take my class. Why should you use clusters? So cluster computing is useful for certain types of problems. Here's some examples. Problems that are too big to fit in one laptop or workstation because of limitations of memory or number of cores. So you might be running a simulation on your laptop and you say, double it, and your laptop says, I'm out. I got no more memory available for you. Then you need bigger machines. And you know, we have huge machines, as big as you need, basically. And then the next type of problem is problems that scale well with more CPU or cores or memory. So an example would be like, you have to do a million things, but you can do them in any order. Then, you know, 2 CPUs could work on it independently. 4 CPUs could work on it independently, all the way until you get to like 1,000 CPUs, and then maybe it's not worth it anymore to add more CPUs. So depending on the type of problem you're doing, that may or may not be the case. Only you know how your research works, but it's very common. Almost all problems these days can be divided up into sub-problems for different CPU cores to work on. Single-threaded problems with millions of permutations. So that's like a more mathy way of saying the same thing I just said. If you like math, then you know what a permutation is. And then the last one is problems that require large high-speed storage and or interconnect. So an example would be something like if you're working with real, like live weather data. Weather data is enormous. You're downloading like the entire planet worth of data. And so maybe your laptop at home has a weak internet connection and it can't handle it. Then sometimes it's not about the resources. Sometimes it's just about where they're located. The university has really fast internet. We're connected directly to Houston, and Houston is connected directly to someone else. And like, you know, we're right on it's like the Texas backbone or something. We're right in the middle of it. So sometimes you need high-speed data, and we can do that too. So a cluster diagram, cluster has many components. They all have to connect together. So here's a diagram, a really simple version where I just tell you like the 4 basic kinds of elements of a cluster. So the first element here that's green is called login nodes. The login nodes are the ones where you do your basic tasks like moving files around. So login nodes do stuff like that. And then, so where are the files? So the files are in a shared file storage. The file storage is actually not attached to the login nodes. So whenever you're moving files around, the login nodes are communicating with the nodes where the files are physically actually stored. And then, but the login nodes, there's only a few, so we share them. If you want to do computing, then you need to get on a compute node where you can have it all to yourself. Nobody else sharing that with you. The compute nodes are connected to the same shared file storage. So if you set up your files on the login node, they will be there also when you're on the compute node. So that's one less thing to worry about. And then if you want to give instructions to a compute node and walk away, then the way that we handle that is we have a scheduler. You create your instructions, you give the instructions, you do this on a login. You create your instructions, you give them to the scheduler, you walk away. Eventually, the scheduler finds a compute node for you, passes your instructions onto that compute node does the work, you're long gone by that point. So that's how we make sure that everyone is, sharing the compute nodes and not crashing into each other, and they have a fair chance to get a compute node, is we use a scheduler. So you normally can't get on a compute node directly. You normally have to use a scheduler to get to the compute node. Now you still can get an interactive, yep, Keith found what faster means. Good job. Thank you, Keith. I literally didn't know that. So if you like interactive where you just type in commit and execute one command at a time, you can still do that on a compute node. You just have to go through the scheduler to get to the compute node. And if you want to, I'll show you how to do that. It's not really a big deal. Now, how about a slightly more detailed version of this diagram? So there are multiple login nodes, but not very many. So they will literally be numbered 1, 2, 3, or 4. I think Grace has 5 of them. Faster only has 4 of them. Terra has, I don't remember how many. I think Terra has 3 or 4. But the compute nodes, there's hundreds of compute nodes. So like, we don't even remember the names of all of them. They're just like some random letters and numbers. Some of them, most of the compute nodes just have memory and cores, but some of them have other hardware like GPUs, double extra memory, stuff like that. We talk about shared file storage. There's actually 2 of them. One is named home. That's a small location, but very fast. And the other is named scratch. That's a large location, but a bit slower. So depending on your application, you might be splitting your files among those 2 places. And as long as you're within the limitations of the file system, then you can use whichever one you prefer. But there are limitations, so we'll go over those later. So about those clusters, so Terra has 307 nodes with a total combined 8,512 cores. Grace has more. Grace has 925 nodes with a total of 44,656 cores. And Faster doesn't have quite as many, only 180 nodes with 11,520 cores. The reason for Faster being more powerful than Grace is not because it's not because it has more, but because what it has is per unit individually faster. And also it can do some neat tricks. So a typical node on Terra, not all nodes are identical, but a typical node on Terra has 28 cores and 64 gigabytes. So that's already bigger than a workstation. A typical node on Grace has 48 cores and 384 gigabytes, which is a bit bigger than Terra. And then a typical node on Faster has 64 cores and 256 gigabytes. You might be like, wait, that's less memory. You don't have to worry about that because Faster has neat tricks. You can get more memory. So all 3 of these clusters have GPUs. Grace has more kinds of GPUs than Terra has, I think. But Faster has a neat trick where their GPUs and the memory are what's called composable. That means when you request a node, you can request additional resources to be attached to that node. And in real time, the cluster reconfigures itself in such a way that that node becomes a thing that exists. Now, currently, we're doing that by hand because not all the features are working, but eventually it will be autonomous, where you don't even have to ask for permission. You just, you submit a job, and then whenever the resources are available, it builds a node for you virtually, somebody's not going in there and unplugging things. I have a whole presentation about how that works, but we're not doing it today. All 3 clusters use the Slurm job scheduler. If you've never heard of a job scheduler, then that doesn't mean anything to you, but that's not important. And if you wanted to check about these facts, you would go back to the webpage or the wiki. They both have these same facts. So here's me showing you that if you went to the wiki, you could find these same facts. So on the left, I have the main page, a little snippet of it. And on the right, I've navigated to the Terra intro page, which says, here's some fun facts about Terra. And you can see that there's a table with facts like how many nodes and how much memory are on each, how many cores and how much memory are on each node in the Terra cluster. And there's one for Grace and there's one for Faster. So if you like go, oh man, I need this much memory, I dropped it. If I need this much memory, what node will do for my purpose? Then you can go and look at the table and figure out which nodes will work for you. Getting started. So I've already talked for some amount of time. We're gonna have you do your activities now. So the first thing you need to do is you need to get connected to the HPRC resources, and connecting starts with authenticating. So we authenticate using the TAMU Central Authentication Service, which is the CAS, and that's the thing where you have the two-factor authentication. Now, whether you are using your terminal, so if you like terminals, you might type SSH if you're using the SSH protocol to connect, and then it will prompt you to do the two-factor thing in your terminal. Or if you're in your browser, then it'll show you a browser page with the same information, but it's more beautiful to look at, which is that you have to do your two-factor thing. So I will go ahead and I'll do an example for you. We're going to do the web. I'm going to do the web login example, but it's pretty much the same if you do a different example. I guess a couple slides from now. So I said that there was a home and there was a scratch. You need to know what the limits are. I said that home was smaller but faster. What do I mean by that? So in your home directory, which we have a variable that stores the location of your home directory, so you can type it more quickly. In shell language, that's $home, which means it's a variable. So the value of the variable is equal to the location of your home directory, which is /home/ your net ID. So this can store 10 gigabytes and 10,000 files. That's actually not a lot in terms of research. 10,000 files probably won't handle something like, a full research project where you have to do something 10,000 times, output one file per each of them. So that's where you would store things like configuration files, where there's just one for your whole project. Or if you need to install some software, you need that software to be fast, because files that are part of installed software, you need to read them quickly so they don't slow down your performance. You put those in your home directory because the home directory is fast. Then we have the scratch directory, which works the same way. The scratch variable is short for your location on disk that's for you, scratch /user /your net ID. That one has a much larger limit of 1 terabyte and 250,000 files. If you have a reason that you need more, usually because you're on a research project and your PI says, this research project is important, you need more, then you can actually request more and temporarily, or if your PI wants to pay, then you can get it more permanently. But that's the one where, the upper limit is based on your need rather than just technically speaking, because the scratch file system is designed to handle very large volumes. It's not a long-term storage area though. That would be called archive. And some of our older clusters actually had a dedicated archive, but Grace does not. So if you need long-term storage, you will have to get some kind of solution that's personal to you, like a server that you own, or you can make a deal with us where you say, I need it for this amount of time. And then we say, yes, you can use it for this amount of time. But you should be like doing research on your files, and then when you're done, we delete them because again, these file systems are shared among other users and they need that space too. And here are the some facts that I just said. So these are your personal directories that have your net ID. You can also have group directories. If your PI has a research group of like 5 students, you can share a directory that's got his name, your PI's name, his or her, your PI's name instead of your name, and then do all that. Your whole worth of students can share that directory if you think that's what's useful to you. You should not be sharing your personal directories because that constitutes more or less the same thing as sharing your password, because your personal directories will hold information that's like sensitive. If you need to know how much of your space you've already used, there's like 2 ways to do that. The first is the show quota command, and the second is in the browser, I'll show you a page where you can do how much files you have already used. Okay, now it's time for you to log in. So I'm going to use the portal to log in, and we're going to take a look at these file systems I've been talking about. If you do not like the portal for some reason, the exercise is just fine on the command line, but I do recommend the browser. So I'm going to hop on over to my web browser, and I'm going to go to the portal. There should be a link around here somewhere. I lost it. All right. So from the main HPRC page on the right, there's portal, and I'm going down to Grace portal. Oh, it already logged me in. Why did it do that? I told it to log out. All right, well, I'm going to log in again because I want to show you how it works. I logged out again. I'm going to try to get to the Grace portal. What is going on? I log out. I say log out. Close your browser. Fine. Close my browser. Ridiculous. Okay, so I clicked on the link from Portal Grace portal and ended up here. This is your normal central authentication service page where you type in your net ID and your net ID password. And then it prompts you to do the Duo authentication method. You can see that I have Duo set up on my phone where I just tap a couple of buttons on my phone and then it finishes logging in. That's my recommended method for you. You can choose, there are multiple methods, but they all involve something. Okay, so I said we're going to talk about those file systems. So can you please raise your hand in chat or in real life if you have successfully logged into the portal? Okay. Anybody in chat? Okay. Please do log into the portal to follow along with our exercises. The first exercise we're going to do is, well, first I'm going to tell you what the portal, what the menu options are. So across the top of the screen, we have the Files menu, which is used for copying and editing files on the cluster's file systems. There is a kind of primitive text editor, so you can directly edit a text file. You can also upload and download files and do other file operations just by clicking. If you prefer doing file operations by command line, of course, that's always an option. We have a Jobs menu where you can check out what's going on with the scheduler. You have a Clusters menu, which basically the purpose of this menu is to get you a command line on a login node. If you want to do some command line activities, we'll do some of those later. The Interactive Apps menu is like, that's the all-star of the portal. That's the reason why we have it. That's so when you want to use graphical software, something like MATLAB or one of those chemistry simulators where you can drag the atom around. It's so much fun. So you open those up directly in your web browser. No SSH tunneling nonsense required. And then the last one is the dashboard, which is the dashboard is what we're going to do first. That's where you view your file quotas, how much of the file space you've used. So, well, we're going to do that next. So first exercise is upload a file to Grace in the portal. So here's the portal. We're going to use the files menu, and you pick one of your two file systems. So do you want to upload to your home directory or do you want to upload to your Scratch directories? Okay, so we're going to try uploading to Scratch. So when you click, you have to wait a moment, but you get a file navigator. See, we have folders with names and then a bunch of buttons, and I found an upload button that's blue. So I'm going to click on the upload button, and we just, I don't know, we'll just grab any random thing that's laying around. I don't think there's anything even here. I'll just make a new one. There we go. Upload one file. Yep, there it is. Successfully uploaded to the Scratch file directory. Scratch file system. My personal Scratch directory. There we go. So raise your hand if you've gotten this far where you can use the file navigator. Okay. Now the next thing that we're going to do is we're going to check your file quota. So up in the top, we have these menus. We previously used the files menu. Now let's use the dashboard menu. Clicking on Grace dashboard. You have to wait a moment. Grace dashboard actually has a lot of stuff. The first thing we're going to talk about is the box named disk quotas. In a minute, it will load and show me how many files I have. There we go. So it's showing me that on my home directory, I have used 4% of my file size, and I've used 88% of my file count. And on Scratch, I've used 28% of my file size and 61% of my file count. And there you go. And there's a button for request quota increase. So you ran, error, you couldn't create any more files because your quota says no. You come here and you click this button and you get your form that says, do you need to request things? And then let's say hypothetically, I read this and I said yes, then it would, it leads me down a questionnaire of what information you need. As you click, you get more questions, and that will help you to fill out the form to request increase of storage. This is one of those features we're proud of that we developed to make your life a little bit easier. Raise your hand if you've seen your file quota. Okay, so that's enough of that exercise for the moment. Next, I'm going to talk about software infrastructure. So on your personal computer, you can just install something, and it usually just works. The problem with a shared cluster is if everybody's installing their own things, then it's going to take up a huge amount of disk space where it's the same thing owned by multiple people taking up redundant disk space. And also installing things isn't necessarily easy. So people are like, can you help me install this? And we say, yeah, actually we can do that. So we tend to install most software for you. You can install things yourself, but it's not the intended purpose. So we install things for you, and that means that we have to keep track of all the different versions and build options that we have available. So, some softwares, let's see, I should just read what's on the page. So we have a list of what softwares we've installed. So if you go to the web page on the wiki, and there's a software page in the wiki that says what softwares we have installed, you can read about them. We do have license restricted software. So that would be where you have to share a license that the company provides, and then we have to take turns sharing that license. Yeah. And then we install a lot of software for you, but sometimes you want to install it yourself. And you can install software in your home or Scratch directory as long as you do not need the sudo command to do that. Sudo is the I am the root owner of this machine command, and you're not the root owner of our shared clusters, because if you were, you would be able to delete other people's stuff. So you obviously can't do that. If you do have software where it absolutely needs sudo to install, your options are either ask us to do it, or you can take my course called Containers, which is coming up in a couple of weeks. And with the Containers option, you can actually use softwares that normally would require sudo. So the computing environment, so the basic element of a computing environment in Linux is a variable, and the most common variable is a path. So path is the location on disk where an executable or library may be found. So if you are installing software, it's going to go into like a default location where your operating system expects it to be. But we can't put everything in the default location because we may have like a lot of different softwares that don't interface with each other. So you have to know which one you're using. And if we put them all in the same directory, you won't know which one you're using. So we have to be able to change the path variable to reflect the actual location on disk where the version of the software you want to be using is located, and not simply some default location. And since there's a lot of software with many versions and many paths, we have to be able to manage all of these software versions. So we have a strategy for that. The strategy is using what's called a module system. So we're using a module system named LMOD. And so each version of a software or application or library is available as a module. And a module, basically, more or less, it's one-to-one with you installed something and there's a module for it. How does this happen? I made the presentation and these curly braces lined up with these words, and then I downloaded it and now it looks different. Why are they messing with me? Why?
It's still normal on the PDF.
So in the PDF version that you're following along, it looks fine. But in this PowerPoint that I'm displaying right now, this is messed up. I am frustrated. Okay, so suppose somebody wanted to install TensorFlow, which is a software, and then so the name of the module would look like TensorFlow / and then a version number. And then if there's any more information about how it was built, like this version of TensorFlow depends on this version of Python. Dependency is a common build option. That means you install this one first and then you install this one. So if there's a dependency, then it would be after the version separated by hyphens. And then loading a module means adding the location on disk where this was installed to your path variable so that whenever you want to use it, your operating system knows where to find it. So that's what loading a module means. And the reason to use a module system like LMOD is because it handles loading dependencies. So you go, I need TensorFlow. LMOD knows you also need Python. So it also loads that into your path variable. So now you get everything you need to make this software work with a very small number of specifications. You have to specify, but the amount you specify is hopefully minimal. So in order to use LMOD, you have to know a couple of commands. So the LMOD commands start with the keyword module. So here are three: module avail, which lists modules that exist that you can use. Module spider, which searches for modules that match a keyword. And module load, that loads a specific modules variable loads a specific module into your environment. And then we also here at A&M have a shorthand where we type MLA, which is short for module available, but it's a little bit smart. So if you do MLA space module, then instead it does module load. So, you know, you might save a few keystrokes if you just go with MLA. Most of the time, it works better. But if you got confused, you can go back to the regular module commands that just do exactly what they do. If you want to read about what modules are available, we have a web page for that. So we have a web page for learning about module commands. So that's this one, Wiki Software Modules. I'm going to go investigate it now. So if I go to the software page, then I can read about, then I can go to the module page and I can read more about how to use these module keywords. So I showed you like the main three, but there are more. You can see there's list, unload, purge, help, swap. I mean, you can get fancy, but we're not going to need any of those for today's exercises. And then the other web page is, instead of on our wiki, we have an actual dedicated software page. So that would be over here. So our software page, that's not it. There it is. Nope, that's not it. Why am I confused? Maybe I should just use the link that's in front of me. There we go. Is this page going to load? Apparently that page doesn't load. Yeah, that's the right link. It's just not loading for some reason. Can anyone else get this to load? Software Grace. Oh, it does load. It's just slow. Okay, there we go. Yeah, the link works great eventually. So the point of this page is that it's like instead of going to the command line and typing commands, you have a graphical method. So you can just go, I want to learn about TensorFlow. That was the example I showed earlier. And it says, oh, these modules have the word TensorFlow in them somewhere. In fact, this one is actually named TensorFlow. So then you could click on it and learn more. But for our exercises, we're actually going to be using the command line, because when you go to submit jobs, it will look more similar to command line. So there's actually a reason in this case to do it that way. Okay, so I said we have a module system, so our modules are organized. You know, we don't just throw them all on the floor. We put them into categories. So we have a module hierarchy, and the way that we categorize our modules is we group them by their dependencies. So the core modules are called tool chains. Those are the most common dependencies. So for example, it might be a compiler. So if somebody wrote code in C and then hit compile, then the executable that comes out depends on the libraries that were part of that C compiler. So that would be a dependency. And therefore, so core module tool chains are more or less, you can think of them like the compilers that were used to build the executable. Toolchain dependencies are not included in the module name. So let's look at these two module names. They look the same, number 1, number 2. We have lamps, which is, what is lamps? Lamps is a molecular simulation software. The name escapes me for the moment. So somebody installed lamps, and the version of lamps is from the 3rd of March, 2020. But they installed it 2 different ways. First, they installed it using the free open source compilers. So in Linux, there's like a new foundation, GNU, and they own a bunch of stuff, including some compilers. And so the tool chain's name is free open source software, and the free compiler is in there, among other things. And then somebody else installed LAMPS using the Intel compiler. Intel compiler is not free, you have to pay money for that one. Usually it's about the same, but sometimes it's better. We have the Intel at A&M because we did pay for it. So you can use the Intel compiler. You can use software that was compiled with Intel compilers. But generally, software that was compiled with it is not compatible with software that was compiled with the free version, the new foundation software compiler. So here we have two modules, and they actually have the same name. You can see that the module name ends here with Cocos, which was some kind of build option. And then, so you can't tell these two modules apart just by their name. You have to know how they were compiled. And so that's why the tool chain is part of the hierarchy. So we organize these by separating them into categories based on what tool chain you used. And that means how do we go about loading this module? Next bullet, the tool chain module. So these are module names. You can see they have the slash notation. The toolchain module acts as a gatekeeper. You must load the toolchain first in order to gain access to the modules that depend on it. So if you wanted to loan, why can't I speak? If you wanted to loan, oh my goodness, 3 times in a row. If you want to load the module after bullet number 1, first you would load the FOSS module, then you would load LAMPS. If you wanted to load the module after bullet number 2, first you would load the Intel module, then you would load LAMPS. And so the fact that you already loaded the tool chain is how you specify which actual module of LAMPS you're going to get. Okay? It takes a bit of getting used to, but we tried it the other way and it was a mess. This way is very clean. Using a hierarchy where you have to load your tool chain first means that it's almost impossible to accidentally load things that are not compatible with each other. Because if you try to load something that's outside the current tool chain, it doesn't exist to you. You go, I don't even know what that is. You can't load it until you load the tool chain first. So so I'm showing you an example. So here's an example of, I need to load Perl. Perl is a programming language. So you need to load Perl to do some kind of Perl programming. The first thing you want to do is see if Perl is available. So MLA Perl, and it's going to check to see if there is a Perl. And it's going to be like, yeah, there is one. And then, so the next thing you need to know is you need to learn how to load it. Every module, most modules depend on a tool chain because of the hierarchy. So then you would use module spider to search for a particular version of Perl, and then it would tell you, here's how you load this version of Perl. You need to load this tool chain, and then you can load this version of Perl. And once you have that information, then you're ready to do your module load command. Module load, you can load multiple modules on one line as long as the tool chain comes first. So module load, and then here's the tool chain that this Perl was actually built on top of, and then the Perl module itself, and then you get a fully functional environment where you can use Perl. And there was the extra step of looking up the tool chain, but doing that prevents a lot of mishaps. So it's worth it. So let's do an exercise. We're going to open a terminal on Grace in the portal, or by your favorite method of opening a terminal. If you've got a different terminal on your local machine and you want to SSH in, it works great. But I don't feel like it, so I'm going to use the menu, the clusters menu, and click on the Grace shell access, and I'm going to get a terminal on a login node. So over here, close some tabs. Got too many tabs. I'm going to click on the clusters Grace shell access. And now I have a prompt to log in. It works the same way as the other login. Just gonna provide my password for my net ID. And then it's gonna prompt me to do the Duo two-factor thing. So once again, I have to use my phone. And I get a command line on the login node. So this login node is Grace1. You can see down here, it says Grace1. My net ID is this thing. Grace1 is the login node where I ended up. And tilde is short for my home directory. In case you are not super familiar with Linux, that's just what it is. So I'm in my home directory on the Grace1 login node. So let's investigate some module. Let's investigate some modules. So raise your hand if you've got a shell on Grace. Okay, I call it a shell or a terminal because my brain goes too fast, but they mean the same thing to me. I hope you're not too confused yet. All right, so the exercise, oh my, you can't even, PowerPoint messing with me. I have to fix this. We can't keep working like this. What the heck is this? Why doesn't it work? I think I know. I think it's because the tabs got bigger and the letters didn't get bigger, and that's why it doesn't make any sense. Okay, slideshow. Here we go. That's workable. So the exercise that we need to do is we need to investigate the BLAST plus module. We're going to try to load the BLAST. You're gonna pick a version, and I picked for this exercise 2.8.1. So we're gonna try to load it, and it's not gonna work because I said the tool chain acts as the gatekeeper. If you try to go around the tool chain, you hit a wall. It's not gonna work. So let's try it. So module avail BLAST plus. It said, I didn't find anything like that. Well, that's probably because I should have done module spider. Module spider BLAST plus. Okay, so it says, yeah, we have some of those. We have some BLAST pluses, and here are some versions that exist. And then it says, oh, and if you wanted to know about one, that's what you would do. So if you're on the command line and you see that thing on the bottom that says like press any key to see more, but you don't want to, then you can just use Q to make it go away, get your terminal back. So let's learn about the 2.8.1 version of BLAST plus. It says you'll need to load these modules before you can load BLAST plus. So the exercise was, what if you just try to load BLAST plus without doing the tool chain? It says the modules exist but cannot be loaded as requested. And it says try module spider to see how to load the modules. So your exercise is filling in the blank and with the correct tool chains in order to load the module. Please give it a try and let me know if you successfully load the module. Yeah? So how do you know you successfully loaded the module? So we have the module list command. Oh, it's because I didn't actually do it. Haha. All right. So the answer to the exercise question was module load, and then these two tool chains, GCC and OpenMPI, and then finally Blast Plus. How do you know you've done it correctly? You have the module list command. It says currently loaded modules. So I requested 3 modules explicitly. 2 of them were tool chains, those are the gatekeepers, and then the thing itself that I wanted. But what I actually got was 22 different modules were loaded. And that is the benefit of using a module system. If you specify what you want clearly, it will do all the work of finding these other modules that it knows you need and loading them as well. So you get a totally complete and consistent environment with minimal specification. Any questions about how that worked? Anybody in chat want to say a question? Let's try breaking it. What's the fun of doing it right when you could do it wrong instead? So we already loaded a GCC module. That was the tool chain that a specific version was needed. What if we then go and load a different one? Module load GCC 10.2.0. That happens to be my favorite. What's going to happen? Any idea what you think is going to happen? So let's read what happened. So the first thing it says is there are some inactive modules. The second thing that's happened is this module is reloaded. And the third thing that happened was these modules were reloaded. So we used to have GCC 7, now we have GCC 10. Good, because I asked for GCC 10, so I'm glad I got what I wanted. It unloaded the other version of GCC because you can only have one. If you try to load 2 versions of the same software, then you have an ambiguous situation where your operating system doesn't know what you're doing. But you'll see that the Blast module I loaded became categorized as inactive. Let's check module list. It says I have loaded modules, but only 4 of them. These other 18 modules became inactive because I no longer have the gatekeeper loaded that I need in order to access them. And module system knows that. So it's not going to let me try to use these modules without the correct tool chain. It would, if you did try, then it would just break. It would literally crash. So even letting you try is a bad idea. So it's not going to let me try to use them in the wrong way. So that's why the module system is fantastic. And then whenever you're done playing with modules, you should execute module purge, which is just a shortcut for unload all modules. How do you know it worked? Module list, no modules loaded. Any questions about module hierarchy? Should we investigate that path variable? I made a big deal about the path variable. Why don't we check it? So let's see what's in the path variable. So in the shell language, you investigate variables by doing like echo, which just means print on screen. And then the way you access the variables with $. So if you echo your path, you'll see there's a colon separated list of directories. And these are all like default directories, things like your home directory, the local software bin directory. None of them are specific to any particular software. And then if we go ahead and load a module, now let's take a look at that path variable again. And you can see that the list has increased. In addition to all the stuff that used to be there, we have 2 new directories. We have a GCC bin directory and also this bin utils bin directory. Let's check what modules got loaded. 4 modules got loaded, and you can see this bin utils module corresponds to this bin utils bin directory in the path. So that's why that's there. There's some executable there that's coming from this module, and the module system thinks you might need it, so now it's in the path. Great. I mentioned another variable on screen, but I didn't read it out loud. I'll just show you quickly. The LD library path is where libraries are stored. And you can see that that one also has some directories like the zlib. So we see the zlib module got loaded and its directory is now in my LD library path. So if I need a library from zlib, that's how I'm going to get it. Any questions about how that works? If you've seen Linux before, then you're not confused. If you've not seen Linux before, you're like, what is this sorcery? Okay. I think I want to take a break because we've already been here for an hour and I forgot to take a break. When did I say I was going to take a break? I said I was going to take a break after the cluster overview, but then I didn't do it. And now this is pretty much like in the middle of this. This is where we are right now. We are in the middle of learning about the computing environment. The module system is the most important element of the computing environment. So we're in the middle of this and we're going to take our break. Howdy students, welcome back from your break. I'm waving to you on Zoom if you have me up there. Hi. So we saw an example of a tool chain, and now I'm going to talk a little bit more about tool chains. Show you some more examples basically. So tool chains are combinations of compilers, MPI libraries, and highly optimized math libraries. So primarily, the components of a tool chain are either Intel or open source. Open source is free, and pretty much the whole open source community gets together and pools their efforts. So there's usually only like one flagship free version of something because everyone contributes to the main flagship thing. So the free stuff is all quite centralized despite being free. And then you have the Intel stuff, which they make and sell, and we do purchase. So you have access to Intel stuff. And then, you know, hypothetically, there could be other tool chains that we did not purchase, but those are the main two that we have. So if all you want is the compiler, that would be the GCC core module or the ICCI Fort module. So that's basically a module that contains all the main compilers for all the main programming languages. So that's like, you know, C, Fortran, Python, a couple others. I don't know. I assume there's more. And then if you want MPI, there's a couple different flavors of MPI. Obviously, so there's a GCC MPI and there's an Intel MPI that you can mix and match. So if you want the free compilers and the free MPI, then the name of that module would be GOMPI. And if you want the Intel compilers and the Intel MPI, the name of that would be IIMPI. And if you are mixing and matching for some reason because you're, I don't know why you would do that, but some people do, then you have IOMPI, which is the Intel compiler, but the free MPI. And then you have all these math libraries. So MKL, BLAS, FFTW, and LAPACK. Those are libraries for doing really fast math operations. So they're technically beyond the scope of just a compiler. So they live in a separate module. And normally when you want those, you also want MPI, because what's the point of going fast if you can't go big? So if you want the compiler, the MPI, and all those math libraries, then the open source one is the FOSS, free open source software. The Intel source is just Intel. So like the default Intel is you wanted all of it. That kind of makes sense. And then you have the mixed source IOMKL, where you wanted the Intel compilers, but you wanted the open source math libraries. I don't know why you would do that, but it's available. And then finally, if you need to be using a GPU, most of our GPUs are NVIDIA GPUs, and the programming language for NVIDIA GPUs is CUDA. So if you're adding the CUDA compiler to your environment, then the name of that module, you just add CUDA on the end. So FOSS CUDA, Intel CUDA, IOMKLC. So an example usage is you could go module load FOSS 2019B. So because these modules contain a lot of things, they're not, the version of a module isn't so much like a software version as it is just the date that module was assembled. And if you want to know what's actually inside of it in terms of like individual versions, then you have to go to, you have to like either load it and see, or you have to go to an online table, which even sometimes I have to do to remember what's in these modules. And you can learn more about these tool chains on our wiki software tool chains, which covers basic facts like this. Usually you won't be compiling anything, but sometimes you want to compile some code. And in that case, that's when you would load just a tool chain, but nothing else. So module usage practices. Applications installed as modules are available to all users except for the restricted modules. In order to access the restricted module, you have to be a member of a particular user group. Once you are a member of a particular user group, you can load the restricted modules exactly the same way. It's basically just a little flag inside the module file that says, are you in the group? No, abort. Next, it's a good habit to unload your unused modules before loading new modules. So we do have a software hierarchy that will prevent most mishaps, but mishaps are still possible. So whenever you're starting a new task, it's a good idea to unload your modules and before you load your new modules, to make sure nothing funny happens. It is recommended to load a specific software version instead of the defaults. So all the examples I showed you, we module loaded specific versions. It's actually not required in the syntax. You can module load a software by its name only, and it will choose the, the highest version that's available that matches your specification. It's not a good idea to do that because we install new softwares all the time. Maybe your maybe your workflow is working great for you, and then one day we install a newer version of something and your workflow breaks. So that's why you want to always specify versions. So if we install something that's newer, you can continue to use what's working for you. And then here's an important one. Don't put module load commands in your bash RC file. I see people saying, but I always want my favorite modules. Well, the day will come when you want to use a different one and you forgot that your old ones are still here and now they're fighting each other and you get confused and don't realize why your stuff doesn't work. And then we have to come and read your bash RC and go, why did you put stuff in there? We told you not to put stuff in there. So if you want to, it is a good idea to write down your module load commands, but you should put them in a file that you name specific for that task, not just your generic all shells get this file, which is what bash RC does. So you would have a file that's like modules for using Gaussian.sh. And then if you ever feel like you want to use something else, you just don't use that file. And because you gave it a name, it's easy to remember it's easy to realize what you're doing right and wrong. Whereas with the bash RC, it's a hidden thing. You literally can't see it. It's invisible. So you would forget it's there. And then finally, avoid mixing tool chains when loading multiple modules at the same time. This usually leads to one of them not working. And the hierarchy is supposed to prevent this, but it is occasionally possible to make something bad happen, even with the module system, because it's not perfect. So just let the module system is there for a reason. Let it do the thing it's supposed to do. Let's talk about a different kind of software installation, which is called virtual environment. Now, virtual environment is specific to Python. If you're not a Python programmer, then you won't use a virtual environment. But there are analogous environments in different languages. For example, the R programming language has one of these. The MATLAB programming language, I think, has one of these. So whatever programming language you're a part of, there probably is an analogy for this. But we're going to go over the Python one because I'm a Python programmer. This is what I'm most comfortable with. So the basic idea is sometimes the thing you want to install is really small. It's a plugin, basically. And but there's like infinite possible plugins. So maybe we don't want to install all the infinite possible plugins, but on the other hand, it's so easy, you can do it yourself. So then the strategy for that is to set up your own kind of little environment that's isolated, install your stuff in there. Virtual environment is for that purpose. And the reason we do it that way is because if you ever want to start over, you need to be able to put the old environment aside and not have all those things you installed like following you around for the rest of your life. So putting them in a specific place means when you need to do something differently, you have names for that. And so you're kind of like, checking your own self in terms of getting organized. Everybody should be organized. So here's some examples of some packages. A package is like a bundle of plugins for Python. SciPy, NumPy, Jupyter Notebook, scikit-learn. Now we actually do provide these as modules, but for the case of, those are just some common ones. You might find one that is not, that we don't provide, or you want a specific version of it. That's another thing that can happen. You want a specific version, but the one that's in our module system doesn't match, so you need to do something else, and that's where install it yourself comes in. So using the virtual environment feature is how you install your own Python packages. So I'm going to go through this example. In this example, if you don't want to do this, then it's probably fine for you to not do this. If you're like, I'm never touching Python with a 10-foot pole, then you don't have to do this. But on the other hand, probably you shouldn't be so scared of Python because it is a great language and lots of people are using it. And there's a reason for that. So if you don't have anything better to do, you might as well follow along. So I'm going back to my terminal and I'm going to module purge to get rid of my modules. Remember I said that was a good idea? Now I'm going to navigate to my Scratch directory. I have a lot of directories in my Scratch directory. Do I have one for Python virtual environments? I know I've done this before. All right, I guess I'm making a new one. All right, I'm making a directory to put my Python environments in. Make dir Python ends, and I'm going in there. So those are just some standard Linux shell commands. cd, mkdir, ls. If you're not comfortable with Linux, you should go back in time to this morning and take the Linux class that happened earlier today, and then time travel back to never mind. So that's what these are. So that's just creating a directory. And then I'm going to load a Python module. I don't want to install all of Python. I want to use a version of Python that's already installed. So I'm going to use the module system to get access to a version of Python that's already installed. This happens to be my favorite version, the Python 3.8.6 version, which depends on the GCC 10.2.0 toolchain. And also another thing I'm going to do is I'm going to add that to a file, which is easyend.sh, and we'll talk about that in a minute. Okay. Oops. What did I do? I broke it. Okay, well, it did what I wanted. I don't know why it took so long, though. All right, so now that I have now I have loaded a module, I need to create a space to install my Python packages. So that's where the virtual end command comes in. So the virtual end is actually not a standard shell command, it's part of Python. So if we ask, where did the virtual end command come from? It says, oh, it came from the Python module. it's an executable that's in the Python module. So if I do virtual env and then I give it a name, my example env, then what it's going to do is it's going to create a directory in the current directory where I can install things. In a moment, whenever it loads. I'm actually going to make the font bigger. So I forgot to make the font bigger earlier. Why is this taking forever? Are we having file system issues? Are we having technical difficulties? Hey, here's a question for chat. Chat, are you choosing to do this exercise? Okay, so it did eventually finish what it was doing. It said it created a virtual environment and then some fun facts. So let's take a look. It says my example env is a directory. So currently I just created it. I didn't add it to my path variable. Same as loading a module, you have to add the virtual environment to your path variable. And the command for that is the source, which is just a standard bash keyword that means execute whatever commands are in this script for the purpose of adding variables to my environment. So we're going to source a script that's in that virtual environment. Source my example env bin activate. Activate is just a script that adds things to your environment, same way loading modules did. So I do that, and now you can see that my prompt has changed. It has been pre-appended with the my example env reminders to remind you that you have added something to your path. Let's investigate the path. We've already taken a look at a path before. It says the first element in the path is the bin directory of the my example env. So in fact, it has been added to the path. So now anything that I install in there, the operating system will know that's where I need to find it. And I'm also going to add that command to that file I was creating earlier. What was the name of it? Yep, there we go. So now easy env, what happened? Is it slow? I feel like it's just being slow. So I'm trying to read the contents of this file. Easy env contains the module load command, and it also contains the source activate command. And I'll show you why I have done this in a minute. Now, let's pick an example of a package we could install. The example we're going to install is PyTime. By default, we will see that PyTime is not installed. How do we know? Let's open up a Python terminal and try to import PyTime. Wait, is that what it is? Yeah. So no, PyTime is not installed, it doesn't exist, so you can't do that. So let's install PyTime. So the way you install anything in Python is with the pip. Pip is just Python's package manager. Pip install Python time. So where's it going to go? Well, it's not going to go into like the main cluster default area because you're not allowed to write anything there. That would require sudo. Instead, pip is going to put it into the current virtual environment where it knows it's allowed to install things. Pip is smart enough to do that. It says downloading Python time, 2.6 kilobytes. I know you didn't take any time to download that. All right, it's done. So now let's check again if Python has, if we have Python time now. We try to import PyTime and it does not fail. And I'm going to investigate PyTime by printing it. And we can see that PyTime is a module that's located here. It's in my example env, and it, some nonsense, who cares? It's just some Python specific nonsense. The point is it installed into the directory that the point of this directory was it's for installing things into. I guess I'm done with that. And then when I'm done with my environment, I want to make this thing go away. The keyword for make it go away is deactivate. It's gone. All right. So now that I have shown you how to create a virtual environment, I don't want to have to remember the command for activating it. Because remember, when you want to activate the Python virtual environment, you also have to load the module that you loaded when you created the virtual environment. Because the virtual environment itself does not contain everything. It just contains what you installed. So it's not complete. We still need the other things. So we need those module commands. Where did they go? Well, I remember I saved a copy of them in the easy end. So the cheat shortcut is if you just source the easy end, it means execute both of those commands for the purpose of modifying the environment variables in my current shell. Got my environment back. So it's a bit easier. I don't have to remember as much syntax. So that's why I do that. And that's better than putting it in your bash RC because I was able to give it a name and that way I remember that I've done it. So later I don't forget that I've done it. Sorry, I'm a bit pedantic. So I'm going to do deactivate, and I'm going to do module purge, and then we're going to move on with our lives because I'm done with this. It's time to learn about cluster computing. So we've learned about the cluster environment. We learned about the module system. We learned about installing something in your Scratch space. It was specific to Python, but the theory is general. Let's learn about how to make these supercomputers do something. So everything we've done so far has been on the login. In order to get the compute nodes to do something, we have to write down some instructions and pass it over to the scheduler. So we're going to write down some instructions in a file, and I call that a job script file. Now, the name of the file is not important. You can name it whatever you want. But fundamentally, it has to be some kind of executable. Normally, it's a shell executable, a bash script file. So we have a bash script file, which we call job script because we're using it for this purpose. And then we have an operation where we submit it to the batch manager, which is Slurm. And Slurm then reads the script file and tries to understand what it was you wanted. So what goes in there? The batch job script is a text file that contains both Unix commands or shell commands, I guess I should just say shell, and batch manager job parameters. So the batch manager job parameters are like the resources you're requesting to use. Do you need a compute node? How big is the compute node? How long do you need it for? These types of things. Then it will read that and decide, then it will put you in the queue to wait in line for your turn to be on a compute node. And whenever it's ready, it sends your same file to the compute node, and that file is also the executable that the compute node runs to do your work. So you have to put both in the same file. You put the commands to do your work and also the parameters that the batch manager uses to decide how you put your job on a compute node. I said that the batch manager parameters are resources that you're requesting. So what type of resources do you need? You need to request how many processor cores, how much memory, wall time. That's at the end of this amount of time, kill my job. If you don't have that, then your job could run forever, and that's not okay. So wall time is, this is the longest my job is allowed to go. If it goes this long, something is wrong, so you should just kill it. And you can also request other resources like GPUs. And then how do we keep it fair? Well, the more resources you request and use, the more your account will be charged. So we have a billing account, and the unit of a billing account is called the service unit. We call them SUs. So how do you know how many you have? So there's two ways. You can use the My Project command, or we can go back to the portal and browse around the portal. So let's start by browsing around the portal. Hopefully you still have that open somewhere. So if you still have the portal open and you go to the dashboard, the Grace dashboard, we've actually already seen this page. The first box is labeled accounts. and that will tell you if you have any service units available. You normally, when you apply for a basic account, you get 5,000 service units. Might sound like a lot, but in terms of research, it's not that much. So you can see here that I have an account and it has 5,000 service units. Well, it did at the beginning, and I used some of them and there's some left. And you can also see that it's marked as my default account. So that's just a handy way of, if I don't specify an account, then I won't start to use this one. That's my only one, so can't really make a mistake. But you might have more accounts. If you're working with a group and you have a PI and your PI requests a research allocation, then your PI will get like 1 million service units, and then those get shared among all the members of your group. So then you'll have a separate account for that. Where was I going with this? I guess we'll just go back to the presentation. Raise your hand if you have checked your account on Grace in the portal. So the exercise is just go to the webpage and look at it. Yeah, that's it. So you should have a default account, and hopefully it has 5,000 service units or some number. So let's talk about how to calculate service units. So a service unit is basically some fraction of a node. So if you're using the whole node versus you're using some part of a node, we calculate that. And the basic way that you use a node is, so I talked about it, the nodes on Grace have 48 cores. Yeah, I wrote it here. On Grace, a typical node has 48 cores and 360 gigabytes of usable memory. It actually has more memory, but some of it is not for you. Some of it is for the operating system to just stay alive. So you basically get to use some fraction of a node. And the service unit is the proportional amount of a node that would have one core. So if you use one core, then you're using at least one service unit. Also, if you do the math here, you'll see that on average, there's 7.5 gigabytes per core. So if you're using 7.5 gigabytes, that's the same fraction of the node. So that's also one service unit. So this first row here is if you're using one core and you're using 7.5 gigabytes of memory, then you're using 1/48 of the core, and 1/48 of the node. And that is one service unit because it corresponds to one core. Now, if you increase either of those, it's the greater one that determines the service units. So if you request 24 cores, but the same but only 1 gigabyte of memory per core, so 24 gigabytes of memory, then it's the number of cores that is the greater fraction of the node. So that is the one that determines the service units used by that request. So this would be a 24 service unit request. Now on the third row, we have requesting one core and 180 gigabytes of memory. So that's 180 gigabytes is half of this node. So you'll be charged for half of the node, which is equivalent to 24 cores. Even though you're not using 24 cores, you're only using one, you'll be charged for half of the node. So that's a 24 service unit charge for that request. And then the last row is just, what if you want the whole node? You want 48 cores, 7.5 gigabytes per core, total 360, and that's 48 service units. So service units are per hour. So all of these are for 1 hour. And then if you want it for longer, then it just multiplies by the amount of time you requested. So 2 hours, you double service units, etc. We'll take a look at another example in a moment. I think maybe there will be a quiz. Any questions about what is a service unit? Okay. So other computing resources that you can request software licenses. So if there's a software that requires a license, then usually they may say only up to this many users can use it at any given time. So then we have to share. So then we have to have something that knows how many there are and how many are in use and how many are available. So we have the license status script to help with that. Queues. So how long does your job have to wait before it's your turn? So as it turns out, we actually give priority based on what you request. So generally, if you request longer time, then you have less priority. Someone who just wants like a 5-minute job can cut to the front of the line, do their 5-minute job. So then the guy who wants to wait 6 days, he doesn't care if he has to wait 5 minutes. So we have different queues based on how long your job is going to run for. So if you're running a short job, hopefully you don't have to wait as long to get to a compute node. And then other queues are for specific resources. So you don't have to wait in line behind everyone who wants a regular node. If you want a GPU, then you wait in line behind only people who want that GPU. So you submit to a specific queue if you need a specific resource. Otherwise, Slurm will decide which queue based on the resources that you did request. So generally, the only queue you have to request is the GPU queue. Otherwise, you don't have to request a queue, and Slurm will pick the one that's the best match for the resources you requested. The only caveat is some of the queues have different requirements. So if you want the faster queue, you have to make your job fit into the requirements for it. So let's take a look. Here's what the queues were on Terra at a particular moment in the past. They may change over time as we update our cluster. But at some moment in the past, somebody was curious, so they used the sinfo command to check what the queues were. So you can see there was a short queue, and that means that's the one with the high priority to get on a node. So if you manage to get your job into the short queue, you won't have to wait very long to get on a node. That one usually gets on a node in a minute or two. But it does have a time limit of 2 hours. If your job is longer than 2 hours, you cannot go to the short queue. And it also has a maximum size of 16 cores, I think, or maybe that's nodes. I don't even know how to read this diagram. And then you can see there are other queues where the time limit is longer. And then you have some special things down here. Literally, one of them was named special. And that one only certain users could get into by requesting. So they would say, I need this particular node for 2 weeks. And then, the admin would put him in a special queue all by himself, because otherwise there's no possible way to make it work, because none of these have a time limit as high. Well, I guess Xlong does. Okay, I don't know what the special queue was for that day, but hypothetically, that's something we can do with special queues. We can put you in a special queue by yourself if you have a need for it. But generally, you want to be in the short queue if you're actually staying under 2 hours, or you'll just automatically go to the next largest queue. So now that you know what the resources are, let's learn how to request resources. So this is an example of a job script file. So it's a text file, and it's full of commands. So the first command is the standard command that bash script files all start with, the bang bin bash command, which just says this is a script file written in the bash language. And your Slurm job needs one of those so that Slurm knows what language your script file is. And then you have a bunch of these sbatch commands, and these sbatch commands are the parameters for your job scheduler. And they start with the hash symbol because hash denotes a comment in the bash language. So later, when this script gets executed, those are not executable lines. They're considered to be comments by bash, but they're not considered to be comments by Slurm. Slurm reads them and says, oh, I recognize these are the parameters for your job submission. You scroll down with your eye until you hit a line that does not start with the hash symbol, and you get down here to some module commands. So whenever you're ready to start doing your work, you have to set up your environment. So we have your scheduled start with module purge, then you load some stuff, and then you maybe source a virtual environment, And so these are the commands for setting up your environment, and you have to include them in your script because when your job starts on the compute node, it starts from a fresh environment, not the same environment that you were developing in on login, a fresh one, as though you just logged in. So you have to, that's why it's important to write down the commands to set up your environment. And then finally, we have the executable. In this case, I used the // notation to say, execute this file, myprogram.py, just a Python executable. It doesn't, it's just, there's no actual myprogram.py, it's hypothetical. So we're gonna go over like what these individual components mean. And also, if you want to review a file like this one, we have the example o1.job file that's in the directory we're going to look at in a bit. So let's talk about what some of these batch parameters do. So the first one is the time parameter. So the syntax for any Slurm parameter is hash capital S batch space 2 dashes or hyphens, 2 of these things, and then variable equals value. So the time parameter tells you what the maximum wall time for your job is. And then if your job runs that long, it will be killed. And so that's your promise to say, I won't go over this. Actually, Slurm enforces it for you. So the time parameter is mainly used for getting into the short queue, because if you put a time of less than 2 hours, you get to get in the short queue. Otherwise, how long your job actually runs for determines your service units. This only determines when it gets killed because it ran too long. Okay, any questions about that? And then here's a note that says if you're on Terra, you have to specify in units of seconds. So hours, minutes, seconds. Even if you requested 0 seconds after the minute, you still have to type 0. A little annoying. Because otherwise it doesn't know what the unit is, because you see that the unit is not part of this syntax. It's just numbers. The next one is n tasks. So n tasks is one way to request cores. A task means that you will be launching separate processes that each get assigned to a separate core. There are other ways to get cores. This is the most common one. And Slurm won't actually force you to use the core in this way. Slurm just needs some way to calculate how many cores you want. So this is one way to do that. So n tasks equals and then a number. So you might write 1 or 48. Some number of tasks that is the total number of cores your job needs. And then the next, let's look at this next one, SBatch, n tasks per node. So this one, if you need multiple nodes, then you have to specify how many of the cores from your job are going to be on each node. So if you requested, say, 96, that's the double of 48. If you requested 96 cores using the n tasks, but you want them to be on 2 48 core nodes, then you would write n tasks per node equals 48, saying, I want to have a number of nodes that each have 48 cores. And hopefully it's a multiple of this one, otherwise Slurm might get confused. Right? So this one is total and this one is per node. Some of the values are like that. And then let's look at the memory parameter. SBatch mem equals, and then in this one you actually do specify a unit. So you can type a number followed by a capital M if you mean this many megabytes, or a number followed by capital G if you mean followed by this many, if you mean this many gigabytes. Generally they're the same, like it doesn't matter too much, but you do have to request both memory and cores every time. Otherwise Slurm will not be able to know what the correct service unit value for your job will be. So generally, I recommend just if the number of cores is important to you, but the amount of memory is not, then you would just request an amount of memory that would occupy the same proportional amount of the node. So that way you get the most amount of memory for your service units. So in the case of Grace, we saw that they have an average of 7.5 gigabytes per core. So you would just take this number of cores, multiply by 7.5 gigabytes, have that be your memory. And then you know you're getting as much memory as you can without increasing the service unit cost. Does that make sense? Sorry, I'm a lot of words. I said a lot of words. Go ahead and speak up in chat if you have a question. I know I just said a lot of words. Yeah, Gabriel has a question. Please do ask.
Okay, so for me working with bioinformatics, a lot of our software has flags for threads, and I could never really understand what it means. What is the difference between threads and cores and the memory? So
Okay.
yeah, it's just really hard for me to run the software
Yeah,
in the
so
adequate manner.
that is a good question. I said that tasks are one way that you can request cores from Slurm. So a core corresponds to a physical CPU. Now, you can use a CPU in two ways. You can have, in Linux operating system, program executions are kind of hierarchical. A process is an independent execution, whereas a thread is among a family of threads. So generally, if you're using threads, one process will own several threads. When you're going parallel, certain programs will do that in a different way. Some programs just start a bunch of processes. Others just have one process that owns a bunch of threads. And some mix and match. You may have like process with 4 threads and then another process with 4 threads and then so on and so forth. And Slurm has different options for requesting processes versus processes that have threads. And I'm not an expert because I hardly ever do this, but you can tell Slurm, I just want one process, but I want it to have a 48 threads. And there's a way to do that. And then Slurm will go, oh, so you needed 48 cores, got it. For most people, processes, tasks, cores, and threads are all synonymous. But if you are using a program that's doing something with a hybrid approach, then you may have to be more specific how you request your cores in order for the Slurm file and the program to actually work correctly. It can happen where that's the case. I don't really want to go and look it up, but basically, like you can, you would go to the Slurm documentation. You would go to the Slurm documentation and you would find what the correct parameters are to request cores with processes versus with threads. They're not exactly the same. They do end up with the same calculated service units in the end, though. Did I answer your question?
Yeah, thank you.
Okay. So here's some examples where on Terra, let's suppose there are some nodes on Terra that have 28 cores. It's just a little easier if we pick a smaller node. So if we want 28 cores, we could ask for 28 cores all on the same node. That's case A. We could ask for 28 cores, but divided evenly among 2 nodes. That's case B, or even among 4 nodes, that's case C. Why would you do this? Maybe you need other resources besides just cores. Maybe you need cores and memory. And so you want to make sure that all of your cores have access to enough memory. So you want to make sure they're on different nodes. So that would be a use case for this.
then the way you would do that is by varying the tasks per node parameter. So here tasks per node is this the same as n tasks, saying to Slurm, I want all of my cores on the same node. And here we have tasks per node equals 14, meaning Slurm, please only put 14 cores on each node for me. Even though there are 28 total, I need them to be on separate nodes. So that's why and then 28 and 7, the quotient of those is 4, so you would get 4 nodes. And theoretically, these might all have the same number of service units, because service units are per core, not per node. But probably this job is requesting more memory than this job is. Otherwise, I don't know why you would want to do that. So in practice, this one would be requesting a lot more memory and using a lot more service units. Yeah, okay, so our good friend Marinus added something about threads in the chat for our Zoom student. Okay, so I already talked about this a lot. But here are the slides that say on each of these different types of nodes, here's how much memory you should specify. So on Terra, the typical nodes have 56 gigabytes, but there are some bigger ones with 112 gigabytes of usable memory. So you would compute the quotient of 56 and 28, it's 2. You would compute the quotient of 112 and 28, that's 4. And that's how you would do that on those 2 nodes on Terra. On Grace, the usable memory for your typical node is 360 gigabytes. So you do the quotient and you get 7.5 gigabytes per core. But we also have some bigger nodes where the quotient works out to be whatever this number is per core. So this is the mem, that's the total memory. You can specify memory per core or memory per node, but it works differently, and I always get confused. So you should probably just like stick with the one that you know how to do. Otherwise you get confused and end up with requests that don't make sense. So here's a quiz. If these were the S-batch commands for a job, how many nodes is this job requesting? Does anyone remember how to compute nodes? You remember. Does anybody think that the answer is 4D4? I don't know why C is over there, don't ask. So how did you compute D4?
80 divided by 20.
So you saw that there were 20 total tasks, and
80.
you saw that there were 80 total tasks and 20 per node, and you did the quotient. That's just dimensional analysis. We learned that in high school chemistry. All right, you got me. It wasn't a very hard quiz question. So yes, the correct answer is D. This one will go to 4 nodes. Hopefully the 4 nodes have at least 40 gigabytes of memory. They definitely will. Okay, so once you have a job file, you have to be able to pass it to the scheduler and then keep track of what it's doing. So the first command you use is sbatch space the name of your job file. And that passes it to the scheduler. Scheduler says, okay, I'm going to put this in the queue. And then how do you know if it's still in the queue? So we have the SQU, this SQ. Oh my goodness. The word queue, not the letter Q. The word queue is the command for, checking on jobs. And then you probably want to provide the username argument. Otherwise you're looking at everyone's jobs and it's just like, there's 100 of them. You don't want to scroll through 100 of them. So you do SQUEUE space -U space your net ID, and that will list your current jobs to tell you which ones are pending, running on a node, and then when they complete, they go away. if you want to look at the ones that already completed, then you can use the count command, which can show you past jobs that completed. If you have a job that's stuck in the queue or stuck running because you made a mistake, we have the cancel that says, kill that job. So you would just provide a job ID. Oh, I forgot to tell you what job IDs. When you submit a job, it says your job has this number job ID. When you do SQ, it will list them by job ID, the number. So you can check what the job ID numbers are, and then you can cancel using that same number. And here's some more commands. LNU will tell you how much resources a job is actually using. PE stat will tell you. Okay, so LNU will tell you about the usage of a job, but I don't know if that's current or just what you requested. And PE stat will tell you how much it's like actually using, I think, for a currently running job. Also, you can check if other people are using the same node that you're using. If you requested less than a whole node, that's one way to do that. And then there's this other one that I don't even know what it does. It says what it does, but I'm not going to read it. Forget about it. I'm getting tired. All right, so job environment variables. We already know some environment variables because we saw them earlier. The path, the LD library path, and the Scratch variables, those are just Linux variables. They also exist in your job. So your job script will have access to those variables. But also there will be some more that are specific to the job. So once your job file gets executed, a few more variables exist. The most important ones are slurm job ID, which knows the number for the job, and tempdir. So tempdir points to a location on disk at the current compute node that is specific to this job. So that way, if you need temporary place to create files, you know that the job won't be, has a unique place to put files that won't butt heads with another job on the same node. So we highly recommend, also the temporary directory isn't on home or Scratch. You can see it's in the work file system. The work file system is very fast. It's like home, it's fast. So for temporary files where you need to read and write quickly, it's the best way to go. And then after your job is almost done, you just copy whatever you need from work into Scratch. That's the best use case of that. What can you not use it for? Well, it's not unlimited, so you can't put a terabyte there. But I don't think it has a number of files limit, so you can have lots of small files, so that's perfectly good. It's not the best for softwares that do checkpointing because your tempdir will be deleted after the job is over, so that defeats the purpose of checkpointing. So if you are checkpointing, you have to save those in one of the two permanent areas on Scratch. Time for you to submit your first batch jobs. So I showed you a job file, we talked about it. I'm going to give you some example job files, so you don't have to write them. And they're located in the Intro to Grace directory under Scratch Training directory. So you need to make a copy of them in your personal space by executing cp-r Scratch Training Intro to Grace space the location where you want them to go. If you're already in your Scratch directory, you can just name a directory where you want them to go. But otherwise, you can use $Scratch to be the shorthand for definitely in my Scratch directory. So this is a hands-on exercise, so please follow along with me. We're going to go back to our terminal. Here's my terminal. I'm going to navigate back to my Scratch directory. Yep, there it is. CP recursive Scratch training. Don't hit enter until you're sure it's right. Because with CP recursive, if you misspell, you could end up making a big mess. So don't hit enter until you're sure it's right. Scratch training intro to Grace, starts with a capital G, and then my scratch directory. And you double check because with CP-R, you need to double check. Yes, that is correct. So now the intro to Grace directory exists, so I'm going to navigate into it. And there's a bunch of job files we can try. Now we're not going to try all of these right now, but there's more you can try them later, like the instructions are like in the wiki for what you're supposed to do with these. We're just going to try some of them. Can you raise your hand if you have successfully copied the example documents into your Scratch directory? Okay. Anybody in Zoom chat? All right, what if you don't like the terminal? Well, you can accomplish the same thing in your file navigator. So you can there's a like copy move button. So you could navigate to the location, do a copy operation in the browser. I just did it in the terminal because I have the terminal open already. But we could, for example, here's a refresh. I'll just do this one. If we refresh, you'll see I have intro to Grace, and it's full of the same files. So we can read them. Let's read example 1. And if you click on it, you get like a preview. But you can also do, I want to edit that, and you get a new window that's a little text editor. So we can now edit this. So let's take a look at example 1. Example 1 has load a module and then print out a bunch of variables. Okay, pretty simple job. Requests 1 core, requests 2 minutes. That'll definitely go into the short queue. Requests 2 gigabytes. Well, that's not going to do anything. All the nodes have at least 2 gigabytes. So now how do we submit that job? Let's go back to the terminal. Let's go back to my slideshow that I foolishly, oops, well, that was a mistake. So I previously said that the sbatch command is for submitting jobs. So let's submit example 1. Okay. So let's do sbatch example 1. And it said submitted batch job. And then it says you requested 0.03 SUs. It's a tiny job. And now we can see if the job is pending or if it's not pending. So I type SQUEUEU and I see that there's no jobs listed. Those are just the headers. That means it already ran. So let's see what the output looks like. Here we go. We have an output file. I'm actually going to choose to look at my output file in my file navigator. Why is there a refresh button? I want a refresh button. Okay. So here's the output file, and I'm going to read it in the browser because I'm trying to showcase how the browser is useful. So what we have here is it printed out the contents of a bunch of variables. There we go. It did what it was supposed to do, I guess. Was anyone able to find the output file in the directory using either the terminal or the file navigator? Okay. Let's do another example job, I think. Yep. So let's try example 2. But example 2, well, let's read example 2 first. We're gonna submit example 2, and then we're gonna check to see if it's running. So first, I'm gonna read example 2. Example 2.echo numbers.job. So what does it do? It has the same requests as before, 2 minutes, 1 core, 2 gigabytes. This is a cute little bash script. For is a loop, and then sleep means wait this many seconds before going to the next iteration of the loop. So it's going to do 20 iterations of wait a second. And that's going to keep it running long enough that we can hopefully catch it. Okay, we're going to try to catch it running. So here's my trick. If you're in the terminal and you hit the up arrow on your keyboard, it'll cycle through previous commands. So go ahead and execute the squeue net ID so that it's the previous command you ran. Okay, that's important. So you run it again. There's obviously nothing in the queue because we didn't submit a job. Now let's sbatch the example 2 dot, what's it called? Echo numbers, right. And then after I hit enter, I'm immediately going to hit the up key and then enter again to quickly execute. Actually, I hit the up key twice. So I'm going to go enter. I'm going to hit the up key twice to cycle back to the squeue command, squeue, and execute that rapidly in under 20 seconds. So we can see that this time it reported there's a job ID and it's owned by me, and it went into the short queue, and it's only using 1 CPU, and it's currently running, and it's been running for 1 second, and there's 1 minute and 59 seconds left. And I execute it again, it says it's been running for 21 seconds, and there's 1 minute and 39 seconds left, and now it's gone. Was anybody able to see a job running in your squeue command? Raise your hand if you saw it. Excellent. Let's try another method of investigating running a job. Okay. So if you go over to your dashboard, okay, we have the dashboard. I already have it open. I'm just going to refresh it with Control R. That's the keyboard shortcut for refresh this page. And if we scroll down a bit, it actually has a table of recently completed and currently running jobs. So in this case, there's no currently running job, but there are several recently completed jobs. You can see that these are the jobs that we just ran a minute ago. We could compare the job ID. So this one said the job ID ended in 35, and this one, where'd it go? This one says the job ID ended in 35. So there's that job again. It took 21 seconds. So that's one way you can, without having to do too much work, investigate your jobs to see what their status is. Even though you can't see them in this queue anymore, you go, wait, wasn't there a command for looking at historical jobs? Yeah, there is, but who even remembers how to do that? Not me. So you just come over here to this table. It's much easier anyway, you know? Has anybody investigated the dashboard and seen your recently run job? Raise your hand if you've done that. Okay. Let's see if we have any more exercises to do. Okay, let's skip ahead to example 5 because example 5 comes with a quiz. Go ahead and try to submit example 5. It's not going to work. Thumbs down. So the quiz is, why didn't it work? Has anyone tried it? I'm going to go ahead and go over my terminal and sbatch example 5. And it says, Doesn't say anything yet. I'm waiting. It says no. Okay, so how do we figure out what happened? Anybody have an idea what happened? Who has a strategy for learning more about this? So far, all I've shown you is an error message. How do we learn more? We're gonna have to read about it. So let's go back over here to our read about it page and actually read what's in there. Does anybody see a problem with this job script file? Raise your hand when you spot the problem. If you're in the Zoom chat, you can also raise your hand. Anybody have an idea what went wrong with this job file? Let's take a look at the error message. Node configuration is not available. CPU count per node cannot be satisfied. Where was that CPU count per node again? Is it this one? 128. So I'm currently on the Grace cluster. Do you remember how many cores a node on Grace has? It's 48. And I think there maybe was a bigger one with more than 48, maybe like 60 or 80. There's definitely not one that size 128 on Grace. If you want that, you're gonna have to go to faster. Faster can do fun tricks like that, I think. Maybe someday. Okay. I want to do that one. So as a bonus assignment, try to make the insufficient SUs error appear. That's just for fun. You have a question?
Yeah, so what if you get an error that says socket times out on send receive operation?
Very good question. So the scheduler is like one process that has to handle all the users. So if multiple users are sending in requests, it's like, sorry, I didn't hear you. You have to just means try again.
Okay.
You know, it can only handle so much traffic. So if a lot of users are submitting at the same time, then it can miss you. Just try again.
Okay.
Usually on the second try it works.
Gotcha.
If you literally can't submit a job for like more than a minute, then you send in a ticket that says, HPRC, please fix your broken machine. Doesn't work. But it will usually work in under a minute.
I got 3 in a row, so I was.
That's bad luck. Okay, so I'm going to skip the bonus one because there's something else I want to do instead. Let's talk about the job composer. So so far we've seen job scripts that somebody wrote and then by hand, I assume, typed in. We haven't written one yet. And then you went to the terminal and submitted that file. But what if you're like, oh man, that's so much work. Can somebody help me out? Ta-da! Easy mode. We have a page in our portal that will help you to make your job files. Okay? So how do you start? We'll start with let's find it. It's kind of hidden right now because it's a new feature. We'll put it like up front once it's like, fully ready and tested. It's still like, not fully ready and tested, but it's at least, I think, working. We're going to find out. We're going to try it. So let's navigate to the dashboard and oh my goodness. You can tell it's later in the day because I can't, every single word is wrong. I just can't speak. There's a button at the bottom of the dashboard labeled Job Composer that leads to this page. So let's find it. Heading over to the dashboard, scrolling down to the bottom, and we have the job composer button. It leads to this page. So let's do it together. Consider this an exercise, okay? Let's do it together. We're gonna try to compose a job script with the assistance of this thing. So we'll give the job a name. I'm gonna name it test job 2 because I did this earlier and I want to make sure they're different. Environment, we're going to click shell because we only know how to make job scripts that are bash scripts at this time. At a later point, we may be able to do something else. So we're going to make a job script that's based on shell. Module, why not pick your favorite module? You start typing and it auto completes. My favorite module is GCC 1020. Add, boom, there it is. Okay. Wall time. You want to put a wall time in there? Let's have a wall time. You can pick your own numbers. You have to pick a wall time, but it says that it will pick for you. It will pick default of 2 hours. Maybe we just let it be the default. You want a GPU? Go ahead and click the box if you want a GPU. Do you want CPU cores that's not equal to 1? It says the default will be 1. I want 2. Feeling spicy. CPU cores per node, I'm going to leave it blank because I only want 1 node at the moment. Total memory, I'm going to leave it blank because I just want, a little bit of memory. Project account, I'm going to leave it blank because I'm just going to use my default account. Email, why not? That sounds like fun. Let's get an email. Now you'll see that if you are filling this out sequentially, by the time you get down to directory, it has suggested one for you. It says, why not put it here in your scratch? Okay, that's fine. I'll just leave it that way. And then we have to choose a file. So we have to choose an executable script. Remember, job scripts are text files that are executables in Bash. So we need to provide a starting point. Let's go ahead and compose one real quick. So I'm going to go ahead and, because I'm on a Windows machine, I'm just going to create something real quick. New text document. I'm going to name it hello.sh. I'm going to create a okay, so apparently you shouldn't name it hello.sh before you edit it. Just created a problem for myself. So all bash scripts start with hash bang bin bash, and then you just put whatever bash commands you want. Echo hello world. That's my very simple hello world. Save. And so that's I just put that on my personal machine. And now we're going to upload that into this job composer. So now hello. What the heck happened? You're kidding me. Apparently the whole entire box is the button. Don't be clicking random places. So now what do we have? We have hello.sh as an executable. We have some batch parameters, and then we have a submit button. What's going to happen? I don't know. Anybody brave enough to try the submit button? Spinning blue circle. Spinning blue circle. Spinning blue circle. Is it going to do anything? Do I have to click it again? Do I have to wait? What's going on? Oh, a pop-up that says nothing. Well, that's adorable. Okay, and now my job files box on the right changed. Now there's a test job2.job. Let's take a look. If I click on it, it says, it's a file, and it says, here's its location. Remember, it suggested a directory, and I said, okay, well, it put it there. So let's go ahead and go back to the The latest version of the composer, yeah, so we're currently developing this. I just have the version that's in front of me. And by the time you go home and you may get a new version with even more features. Oh, okay. Marina says, instead of uploading a file, I could have just typed my command over here. Oh, well. All right, let's go back to the dashboard and see what happened. Does it submit? I don't know. How about the file navigator? Down here. Where's my file navigator? All right. So I'm going to navigate to that location in Scratch and see what happened. I named it test job 2. I have, there's hello.sh, the friendly, the script, it uploaded it for me. How nice. Here's test 2 job. Let's take a look at it. It loaded the module, but it did not execute, it did not produce the output I wanted. Okay, so I still can't figure out why this doesn't work for me. I tried it earlier and it didn't work for me, and it's still not working for me. That's disappointing. Well, we're almost out of time, so I guess I will have to leave you on a cliffhanger where we'll never know what happened to Richard's job. Okay. So we have other batch job examples, but we are out of time to look at them because it's 4 o'clock. So we'll just get out of here. Bye-bye. So how do you get help? I already showed you about the wiki. You can also email your questions to help@hprc.tamu.edu. We have a ticketing system. You get an automatic reply from the ticketing system. Then one of our student workers will tell you, hey, I see that you have sent your ticket and I will try to get you some help. And then eventually one of our experts will be helping you. Try to send us as much information as you can, because otherwise, we're just gonna have to ask you and waste everyone's time. So, send which cluster you're working on, modules you loaded, all that stuff. And we have physical presence at Henderson Hall over there. We also have physical presence in Blocker Building down the hall that way. Depending on the day of week, people may be in either of those 2 places. And that is the end of our